Hi, my name is Nicholas Harwood, and I study physics here at USAO. And my senior research project was in orbital transfer simulations, where I've made a space mission simulator using numerical modeling. Now, what inspired me to do this is I've just always had a fascination with space, but also these orbital dynamic calculations are very essential for the launch of spacecraft. Nobody wants to set up a whole rocket just for a test run. They're going to go through these simulations first to make sure are trajectory calculations correct? Is it going to end up where we believe so? And make sure that the mission will go according to plan. Now, my simulation goes ahead and simulates the Sun, Earth, and Moon system currently. And I wanted to go ahead and start with basically an orbital transfer from the Earth to the Moon. Space mission I chose for that was the Lunar Reconnaissance Orbiter, aka the LRO, and it launched back in 2009. This spacecraft the goal of it was to go into a polar orbit about the moon, where it could gather valuable lunar data, and due to that nature of the polar orbit, it would enable us to see basically sides of the moon and get images that we'd never seen before. Now, here's a rundown on the left of how the simulation actually works. It'll have the initial conditions such as position and velocity, and then the mass of the objects you want involved. So in our case, it's going to be the Sun, Earth, Moon, and then the LRO spacecraft. From there, it'll go ahead and calculate the initial accelerations using Newton's laws. And so go ahead and get those initial accelerations due to gravity. After that, it'll go down and start with our time step. Now, this simulation runs for a certain amount of time. In our case, the transfer took 4 days, so this simulation runs for 4 days' time. And it'll then split that 4 days into a certain number of time steps. Think of it as little chunks that, as it goes through each chunk, it'll then perform a new calculation. So it starts with the first time step, then it's going to go ahead and calculate the acceleration, velocity, and position of all the objects again. And then it'll go through this process over and over and over again until it's reached the final time, and then all the objects have moved through their according positions throughout that day, or throughout the 4 days. Now, there is one extra thing in here. That's what is leading off to the left. If the LRO has some burns, because it had a few correctional burns along its way to the moon, if the time step coincides with the time of the burn, it'll update the spacecraft's velocity to reflect that, and then continue on with the normal gravitational calculations. And then, like I said, it'll go through until the final time step has been reached, and that's about right here. It'll then perform an error calculation using positional data from NASA's JPL Horizons application. And that's how I was able to compare and validate my simulation to real life. It'll then actually go through and increase the number of time steps and do this whole thing several more times. So what that means is, on our first run through, it was 4 days, split, in our case was 1,000 chunks. And then it's going to go through, and then it's going to increase that to 2,000 chunks, and then 3,000 and 4,000, and do this whole thing over and over until it gets to a time step of 10,000. And what that means is, since it's increasing the number of calculations, we should be seeing better results and lower error, as it's getting an update to the positional data more often. Once all the time steps have been completed, it'll then spit out a graph that we can visualize the orbital transfer with our best time steps. And that's what you see over here on the right. This blue line is the Earth, this green line is the spacecraft, and this orange line is the moon. These red dots are markers of the actual position of the LRO, also from the Horizons application, so I could visually confirm, is my spacecraft taking the correct route? On this slide here, you can go ahead and see the same graph that we saw on the last slide, as well as two other perspectives of the same orbital transfer. So once again, the blue line's Earth, the green line's the spacecraft, the orange is the moon, and then those red dots are just actual points of the LRO for a confirmation of the route. So I particularly like this side view down here because you can really get a good idea on the route it took to establish that polar orbit. It's shot down below the Earth and comes up and under and from beneath the moon to establish that polar orbit, which means it's going to be going over the north and south poles. Usually, spacecrafts will launch so that it's orbiting in the XY plane rather than a polar orbit, as it's much less complex. But for the LRO's mission purpose, this was necessary in order to get those to get those other perspectives on the moon that we wouldn't have been able to otherwise. Over here on the right, you can see a top view as well, and that's looking down from above. And you can see how close it gets to the moon in this perspective compared to the side view. You see there's a bit of distance height-wise about what's going on, so that's allowing it to establish that orbit, but it's literally like right under the moon, as you can see from this graph. Now here's the error in the positions. We had those red dots to visually confirm, but obviously we'd like a quantitative analysis. So here's the positional error. As you can see, there's multiple dots, and each one of those dots represents a full run through of the simulation as the time steps get increased. So here's 1,000, and then here's 2,000 time steps, 3,000, 4,000. And remember, like I said earlier, it runs through those increasing number of time steps so we can see the positional error go down as we perform more calculations. And this graph confirms that it behaves like we expected. There's a steady decrease as you increase the number of time steps. And down here at 10,000, you can see we're at less than 0.002% error. And even at the 1,000, we're at less than 0.02% error. So it's extremely accurate. And the graphs that we were seeing is of the 10,000 time steps. Over here on the right is the Earth and the Moon's positional error, which both came out exceptional as well. The spacecraft did end up the worst out of the three, and my belief on that is that, the spacecraft had a lot more correctional burns along the way. There was a bit more kind of uncertainty in its positions, so that's what led to a slightly higher error, while the Earth and the Moon were strictly under gravitational influence, and so I was able to simulate that pretty perfectly. In conclusion, the simulation was accurate and validated by these results, and this now established a nice foundation that I can now build upon and expand on the simulation any way I might imagine. The error was extremely good, as you saw in the previous graphs, and the main benefit of this is that, while it's not as complex as some of the simulations that NASA and SpaceX might be doing for their spacecraft, those are running on, supercomputers, highly complex, and take, long amounts of time to run. This is conceptually easy to understand, and my simulation only takes, a few minutes to run. So it can provide as a good, quick check for those more complex simulations. And now that I've got this out of the way, I can work on building this into something that is more complex. Some future goals that I have are I'd like to simulate more missions, maybe the Apollo missions or one of the Mars missions, because that would add in a bit more complexity. Like, I need to put in the other planets in the solar system, namely Jupiter, due to its strong gravitational influence on a Mars mission. And I'd also like to do some more things like actually getting into the insertion orbit rather than just the orbital transfer, and maybe improving my system for burns and adding a collision system so I can know if something ran into something else. Right below there, these images that you see were actually taken by the LRO, and this first one is something that is very familiar. That's the near side of the moon. But these other three are the far side, North Pole and South Pole. And those are things that, you've never seen before or would have never seen before without the LRO. And I just think that's super fascinating. I had no idea it looked like that until I looked up these images and, looked more into the LRO mission. And I find it just fascinating. It's like, wow. Those are, crazy looking. But you can find images like these and like hundreds of others on the LRO image website through Arizona State University. And that would be definitely something worth checking out if you're interested by this. Overall, this project has been a great experience. Special thanks to my advisor, Dr. J.C. Sanders, who's been a great help throughout this. And this was coded all in Mathematica. All the graphs and coding was done in there. And I look forward to continuing this, and hopefully another student in the future would also like to pick up on this, and I can hand it off to them. Thank you again for this opportunity. It's been a great experience, and I hope you enjoyed. Thank you.